But suppose, yeah, let's just try to solve this equation. What kind of equation is that? Say it again? This is a linear second order equation, but it's a rather famous equation. I mean, this institute is sort of interested in this equation. This is called the Schrödinger equation. Okay. Q of x is some arbitrary function of x, and this is a Schrödinger equation. This is, you might think, a little bit more specialized than a completely an arbitrary second order differential equation, right? So just for a brief remark here, you know, this is an arbitrary, linear, homogeneous second order differential equation. And you've learned a little bit about these, right? So you learned reduction of order, things like that. In general, this equation, even though it has two arbitrary coefficients, there's a of x is an arbitrary function, b of x is an arbitrary function, this is just as general as this. Do you know why? This only has one arbitrary function, this has two. But I'm telling you that this and this are of equal difficulty.
Because you can always multiply by an integral factor and then eliminate this. That's why prime.
Very good. You're absolutely right. Okay, that's very, very good. So how do we do it? Does anybody know? We can reduce this equation always down to this equation. Always do a reduction from here down to here. Does anybody know how to do it? It's very, very, very simple. All you need to do is to say, let's make a substitution y is equal to some function that we're going to determine, say u, okay, times, say, z. Okay? Now we're going to try to find a function u such that z satisfies this equation. Okay? So all we need to do is to plug him into this equation. Okay? So from the y prime prime term gives you u prime prime z plus u z prime prime plus 2 u prime z prime, right? That's what you get from here, right? And from here, you get a times y prime, which is u prime z plus u z prime. And then you have a b term, which is b u z. Okay? Now, in order to make this equation look like that equation, we don't want to have any z prime term in it. You agree? We do not want a z prime. So let's put the z prime terms here in a box, and we want this to be 0. Okay? So the question is, can you find a function u such that this guy will be 0? Well, u would have to satisfy the equation 2u prime plus au is equal to 0. Okay? So this is the function u that I would like to choose. And of course, this equation I know how to solve. Why? It's just first order. Right. So there's a very big difference between first order equations and second order equations. This equation is trivial. This is not only first order, it's actually separable. It's about as simple as you can get. And to solve this equation, I divide by u and 2. Okay, so I get log of u plus the integral of a over 2. Let's call it of s ds up to x is 0. I could put a constant here, but it doesn't matter. Okay? And so, therefore, u is equal to e to the minus integral of a of s over 2 ds. Okay? So I choose this function to be u. Now this stuff goes away, and the equation that I'm solving is now a Schrodinger equation. Okay? Do you all see that? So this is no more difficult than this, because this equation can always be reduced to this equation. Okay? Now, before I go on, I want to solve this problem using perturbation theory, of course. This is a very, very hard problem. But do you know why it's a hard problem? I mean, does anybody have a feeling for whether this is an easy problem, a hard problem, a very hard problem, extremely hard problem? How do you solve equations like this? Does anybody know?
We can use power series.
Sorry?
We can use power series.
You can use a power series, that's right. And if you do, a power series, first of all, doesn't always work, but it often works. And a series in general works, but you see what you're doing. You're using, you have the mindset of a perturbation theorist. Because the advantage of a power series is that it reduces this problem to an infinite sequence of much easier problems, okay? Because all you need to do is to find the coefficients in the series one by one, okay? But taken as a unit, why is this equation hard? Okay, by the way, yes, this equation is hard. This equation is very, very hard. A first-order differential equation has the form y prime plus a of x, y equals b of x. This is a first-order linear equation. This equation is not a hard problem. This is an easy problem. This equation is really easy. Why is that equation so easy?
Can you use integrating factor?
Use an integrating factor. Okay, good. Okay, good work, Sarah. Terrific. Okay, so yes, you use an integrating factor. And this equation is a routine, standard, easy equation to solve. So all we're doing, and if I take this away, if I take that away, I have a homogeneous first-order linear equation. Okay. So all I'm doing is going from a first-order equation to a second-order equation, which is homogeneous. So is it that big a difference? Just going from first order to second order? It's just one more derivative. The answer is, you bet it is. This equation is fantastically difficult. This is really difficult. I'm just thinking maybe I should take sort of 5 minutes and explain to you why it's difficult, because you generally don't, it's not de rigueur, I think, in differential equation classes to boast about the fact that you don't know how to do something. Okay? But that's, I think, it's worth doing that here, because I want to impress you, I want to press upon you the fact that this is so difficult to solve. Okay? This is not a nonlinear equation, it's a linear equation, but it's still very, very difficult. Let me see if we can go through an argument. Suppose you needed to solve an equation like this. There's really only one, if you think about it very hard, there's really only one way to proceed. To solve an equation like that, what I would do is to write it like this. I would say it is d squared dx squared. Or in fact, let's do this. Let's call d by dx, we'll call that the derivative operator, d. Okay? So that equation has the form d squared plus a of x d plus b of x on y of x is equal to 0. Okay? Now, I can write it in this form because it's linear. Okay, I'm taking advantage of the fact that the equation is linear. So this thing in parenthesis is a linear differential operator. Okay? Now, if you think about it, there's really only one way to proceed. Suppose, this is a quadratic in D. And we know how to factor quadratics in general, because we have a quadratic formula. So the idea is, let's factor this derivative operator. So let's write this as d plus a of x times d plus b of x on y is equal to 0. Okay? So as an example, if I had the equation y prime prime minus y is equal to 0, this equation would be d squared minus 1 on y is equal to 0. Okay? And I know how to factor this, right? You learned factoring, right? Is 899 a prime number?
No.
No, no.
Well, why do you say no?
30 minus 1, 30 plus 1, phenomenal.
Very good. Very smart. Okay, excellent. Okay, it's not a prime number because its factors are 29 times 31. So what you observed is that 899 is the difference of two squares. It's 30 squared minus 1. That's right. Okay, so so I can write this, just as you told me, I could write this as d minus 1 times d plus 1 on y is equal to 0. So I factored it. Okay. Now it's interesting that when you factor differential operators, it's not the same thing as factoring numbers, the way you did. Okay. For example, there's another way to factor this. You could write this as d minus hyperbolic tangent of x times d plus hyperbolic tangent of x. Okay? There's not a unique factorization. When it comes to numbers, integers, factorization is unique. But when it comes to functions, factorization is not unique. It's very interesting. But it doesn't matter. I don't care whether the factorization is unique. I claim that if we can go from here to here, we have solved this problem. Okay? Why is it that we've solved this problem? Well, because once it's written in this factored form, there's no more thinking. Why is that? Because I can call this thing over here, let's give this thing a name, W. Okay? What equation does W satisfy? It satisfies the equation W prime plus a of x times W is equal to 0. Do you all see that? Does everybody agree? So that means I know W. Check. So this is a trivial equation. I can find W. Okay? Now that I know W, I have the equation for Y. Okay? The equation for Y is y prime plus by is equal to W. And we agreed that I know W. Okay? So now I just solve this equation for Y. Can I solve this equation for Y? Yes, I can, because we just agreed that first order equations are easy because all you need is an integrating factor. You see that? So by factoring this equation into this form, I have a sequence of two first order differential equations to solve, and that's trivial. No problem. Okay? So the only hard part is going from here, from this line, down to that line. Okay? But if you need to factor this to get it into this form, there's really only one way to do it. How are we going to get the factors? What I mean, what is it that we have to determine? We have to find out what this function A is and what this function B is. And once I know A and B, I'm done. So all I have to do is find two functions, A, capital A, and capital B. So in order to find those two functions, what do? I multiply out the factors, and I compare it with this, and I'm done. Just, right? Perfectly easy. So let's multiply this out. So d times d is d squared, and a times d is a times d, okay? And now, a times b is ab, but the interesting term is d times b, okay? Because this derivative operator, when it acts on b, either acts on the function b, or else it goes past the function b and acts on y. So I get two terms. I get b prime, or I get bd. Do you all agree? And that is acting on y, and it gives me 0. Okay, great. So I now know, so if I rewrite this, this has the form d squared plus a plus b d plus ab plus b prime, all multiplying y is equal to 0. So that tells me, if I just compare this guy with that guy, I have two equations. I know that a plus b must be equal to little a. Okay, these are functions, of course. A of x plus b of x is little a. So that's what's multiplying the one derivative term. And I know that ab plus b prime is little b. Okay? You all see that? So I have two equations for two unknowns. What could be simpler? How do you solve two equations and two unknowns? There's only one general approach. We solve it by elimination. What else? Okay? So why don't we eliminate, say, a? Let's eliminate a. Okay? So from this equation, I see that a is equal to little a minus b. And I substitute a into here. So that gives me a. Oh, sorry. A b minus b squared plus b prime equals b. So now I have one equation in one unknown. And if I can solve this equation, I'm done. And I'm really happy, because this is only a first-order equation. You see that? So this is, in some sense, a generalization of what Sarah was teaching you with reduction of order. I have reduced a second-order differential equation down to a first-order differential equation. There's only one prime here, not two primes. So I've made great progress. Okay? Now, let's see. How do you work through this? Okay. Ah! Fantastic. Okay. So now, what do we do here? This equation, let's rewrite it. This equation is b prime, capital B prime. And let's put everything on the other side. B prime is equal to b squared minus ab plus b. That's the equation we have to solve. Now, there's only one little problem here. What's the little problem?
It's not linear. It's not linear.
It's not linear. In fact, if this term weren't here, we'd be completely finished, right? Because this would be a first-order linear differential equation for capital B. But there's a b squared here. Does anybody know? So this is a generalization of this equation. This is a linear equation. That is, y prime is something times y plus something. This equation is quadratic. This is b prime is b squared plus b plus something. Okay, so it's a quadratic. And this is a very famous equation. It's so famous it actually has a name. Does anybody know? Anybody know? No? Riccati. This is a Riccati equation. Okay. Now, there is only one approach for solving a Riccati equation, and it's very, very clever. Okay, so let me show you in general how you solve a Riccati equation. Does the word Riccati ring a bell? No? This is a very important type of equation. How do you solve a Riccati? Let me just say in general, how do we solve a Riccati equation? Suppose you had an equation of the form y prime is say alpha y squared plus beta y plus gamma. Just a general Riccati equation. How do you solve a Riccati equation? There's a standard technique, which is to say let y be some unknown function that we're going to determine, just the way we determined this function u over here. Okay? So it's some unknown function times, say, w prime over w. This is called the Riccati substitution. It's very, very clever. Okay? At first it looks stupid. Okay? Let me show you why it looks stupid. If you plug this into the equation, on the left side you have y prime. And when you take the derivative of this thing, you're going to get 3 terms. What could be worse, right? You're going to get a q prime times w prime over w, and then you're going to get a q times w prime prime over w, and then you're going to get a q, a minus q, times w prime squared over w squared, right? It's pretty ugly. Pretty oxymoron. All right, and this is alpha times y squared, which is q squared w prime squared over w squared. And then there's a beta times y, which is q times w prime over w plus gamma. This doesn't look like progress, right? Because we started with an equation that had 4 terms, and now we have an equation with 6 terms. Blech! Except that now if I look at this equation, what's the worst term in this equation? What's the most disgusting, horrible, awful term in the equation? It's got to be this term. Right? W prime squared over w squared. But there are 2 such terms. There's also this. Right? And so I can choose q to get rid of these 2 terms. Okay? So I will choose minus q to be equal to alpha q squared. Okay? And now, with that choice, those 2 terms cancel. So, in other words, I want to choose q to be equal to minus 1 over alpha. That's what I want to do. And now, these 2 terms have canceled, and now I have 4 terms in the equation. Of course, it still looks kind of unpleasant, but you notice that the only thing in the denominator is a w. So if I multiply through by w, this equation would now read q prime times w prime plus q times w prime prime is equal to beta q w prime plus gamma w. And this equation is linear. So I've linearized the equation, which is very, very nice. Okay? So although the Riccati equation is nonlinear, I have now made this equation into a linear equation for w. W only appears to the first power. And in fact, it's linear and homogeneous. Okay? And this may be an equation that I can look up in a book. So if you ever come across a Riccati equation, you linearize it using this technique, and then you have a second-order linear equation, and it may be a Bessel equation or a hypergeometric equation, and you taught them these things, right? You showed them the equation. Great. So let's take our equation and linearize it. Okay? And what we learned is that you should choose alpha equal to minus 1 over the coefficient of the quadratic term. Okay? So therefore, it's obvious I want to choose b equal to minus, the coefficient here is just 1. So it would be minus w prime over w. And that will linearize this Riccati equation. There's just a 1 over here. Okay? So if I plug it in, b prime would be w prime prime over w with a minus sign. And then plus w prime squared over w squared is equal to b squared, which is w prime squared over w squared, minus ab. So it would be plus a times w prime over w plus b. Okay? And as we promised, you see what happens here? This is really beautiful. That guy cancels that guy. The two disgusting, ugly, horrible terms cancel out. You see? And now we have a linear equation, and all we need to do is to multiply by w to get it into a linear form. So if I multiply by w, I get minus w prime prime is equal to a w prime plus bw. And if I put the w prime prime on the other side, I get w prime prime plus a w prime plus bw is equal to 0. And that's, so all I need to do is to solve this linear equation. And if I can do that, then I've solved the Riccati equation. And I have factored my second order differential operator, and I can go back and solve the original equation that I wrote down, that original equation there. Okay? Do you all understand the technique? Perfectly straightforward. Okay. Why are you laughing? Yeah.
Does this substitution have some geometrical meaning? Like, why is this special substitution linear?
I don't think it has a direct, simple geometrical meaning. At least not that I know of. Not that I know of. But it's really an algebraic cleverness. And have you studied any nonlinear waves? I mean, you know the Korteweg de Vries equation and so on? Have you studied a Burger's equation by any chance? You have.
Yes.
Then that's exactly the same substitution. This is a very standard substitution for linearizing nonlinear equations. This is precisely the substitution you use to solve the Burger's equation.
But like when I studied as.
But it doesn't have a simple geometrical meaning, unfortunately. Not that I know of. Okay, so what's the problem here? We have made no progress. We can't crack into this equation. Okay, this is a really, really hard problem. Okay, the reason for saying all this is I want to convince you that what I am talking about right now is a hard problem, a very hard problem. So the problem of solving the equation y prime prime equals q of x y, this Schrodinger equation that I wrote down, or I put a plus sign, it doesn't matter. This equation here, this is a really, really hard problem. There is no way that we're going to be able to solve this problem exactly. There's just no way to crack into it. If we could crack in somehow using clever ideas like this, then you would have been taught it. Sarah would have told you the secret already. There isn't any secret. Nobody knows how to solve problems like this.
What about integral transforms like Lefkowitz?
Doesn't work. Okay? It doesn't work because it works, of course, in special cases, but there's a principle. You ask a very interesting question. There's a principle here, and it's called the principle of conservation of effort. Okay? So if you have a problem, you're walking down the street and a guy comes up to you and he says, "Can you solve this problem for me?" Okay? You might be able to solve it by an integral transform. But if you can, it's just as easy to solve it by some other technique, which takes roughly the same number of pen strokes. Okay, so even if you never heard of integral transforms, an integral transform doesn't do anything really fundamental to the problem. It's just a transform. It's just a substitution. Changes one problem into another problem of roughly equal difficulty. Okay, it's just that in one form, it's not as pretty to look at, maybe. When you do an integral transform, it becomes nicer looking, or sort of something like that. But it can't change the fundamental difficulty of the problem. And that's because when you use an integral transform, you are always using equal signs. That's the problem. Okay? So how can we attack this problem? This is a very hard problem. Yeah?
So with integral transforms, you wouldn't be able to integrate something, or where would?
No, an integral transform is a way of changing one problem into another problem. But it's not a problem of substantially, it doesn't change the fundamental difficulty of the problem. If it's a hard problem, then it's a fundamentally hard problem. If it's an easy problem, it's an easy problem. If you can solve a problem by an integral transform, what is the problem with an integral transform? You see, if q of x, say, were x to the 4, for example, then when you did an integral transform, this would become, the second derivative term would now become, you know, just a second power. If you did a Fourier transform or Laplace transform, this would become a second power, okay, times, say, capital Y, okay? And if you have 4 derivatives, that would become 4 derivatives. If you had 4 powers, rather, this would become 4 derivatives. Okay? So this equation is a hard problem. And by doing an integral transform, we convert it into, this just becomes algebraic, but now this becomes a higher order differential equation. So that definitely gets a yuck. Okay. Okay. No progress there. Okay. So I mean, so if we have a fundamentally difficult problem, there's really not much. No, let me restate that. If you have a fundamentally difficult problem, there ain't nothing you can do about it. Okay. Unless you're willing to give up using an equal sign. Okay, and you're willing to reduce the problem to powers, okay, to a sequence of easy problems. That's the idea of perturbation theory. So can we attack this? So now now that I've told you this is a difficult problem, I'm going to solve it for you. Okay? We're just going to go ahead and solve it. So let's solve this problem. Now this is a second order differential equation. So it takes, let's treat it as an initial value problem. Suppose we have y of 0. Well, let's actually solve it for arbitrary minimum. Let's suppose we said y of 0 is a, and is a number a. Okay, it's not some function. Okay, and y prime of 0 is a number b, and we just want to solve the equation, just completely general problem. How would we go about doing it? Well, we know we can't solve this equation exactly. So let's insert a perturbation parameter. So here we go. In here, I'm going to put in an epsilon. Why am I going to put an epsilon there? Because what is the unperturbed problem? Yeah, and that's one of the few problems I actually know how to solve. Okay? So the unperturbed problem is y prime prime is equal to 0. Okay, and I should call this not y, but y naught prime prime. That's the unperturbed problem. And if I solve this problem subject to these initial conditions, what's the solution? Say again? A plus x. Okay, good. Well, that wasn't very difficult. Now, I assume that the solution to my problem is a formal, Taylor-like perturbation series. So I'm assuming that y of x is the full solution here, has the form sum from n equals 0 to infinity a sub n. Oh, I don't like that. Do you mind if I change that? Because I like a sub n. Let's call this alpha and beta. Okay, alpha, beta, so we don't get confused. Okay. You should never ever do that because it screws up everybody's notes. So when you teach, don't ever do what I just did. Okay. So now this is a sub n of x times epsilon to the n. Okay? And we know that a0, unperturbed solution, a0 of x, is alpha plus beta x. We know that. Okay? Does everybody see what we're doing here? So now, let's take this y of x and plug it into this equation and just proceed. Okay? So the first term in the equation is two derivatives. So that gives me the sum from n equals 0 to infinity a n prime prime of x times epsilon to the n. And the second term in the equation is q of x times epsilon times y. Okay, so that is the sum from n equals 0 to infinity q times a sub n of x times epsilon to the n plus 1, and that's equal to 0. Okay? Now, you know what we're going to do next. We're going to compare powers of epsilon here. Right? But here's an epsilon to the n, and here's an epsilon to the n plus 1. So I propose to lower n by 1 in this equation. Let's replace n by n minus 1. But that means that the limits, the endpoints, have to be raised in order to compensate for that. So I can rewrite this as the sum from n equals 1 to infinity. I raise this by 1, but I lower this by 1. So there we go. Okay? And now we compare powers of epsilon. Okay? What is the coefficient of epsilon to the 0? Okay, there's no epsilon to the 0 here. That is just a0 prime prime is equal to 0. And we've already solved that equation. Right? We know that a0 is equal to alpha plus beta x. Okay? And for epsilon to the n, for the coefficient of epsilon to the n where n is greater than 0, what is the equation that we have to solve? The equation is a sub n prime prime is equal to minus q times a sub n minus 1. That's the equation we have to solve. Now wait a minute. Is this progress? I mean, we have a second order differential equation. Have we made any progress here?
We know A0.
Right. This is enormous progress. Because you see, we already know, this is inductive by nature, right? We already know the right-hand side if we're calculating an. Okay? So we begin by knowing a0. Now if we want to know a1 prime prime is written in terms of a known function of x. And then once we know a1, we repeat the process and we calculate a2. So we've reduced an unbelievably difficult problem to a problem that's utterly trivial. How do you solve this differential equation in general? Well, you just integrate it. It's trivial, right? So an prime, if I integrate this once, is just the integral up to x ds q of s times a sub n minus 1 of s. Done. right? And in fact, to be precise, we need to know what the boundary condition, what the initial conditions are, right? But they're very simple, because you see, our initial conditions in the problem were this. But we have already required that, you notice these initial conditions don't depend on epsilon. So in this perturbation series, we have already satisfied these initial conditions by the function y0. So the initial conditions on all the other functions, okay, on a1, a2, a3, are just that a sub n of 0 is equal to 0, and a sub n prime of 0 is equal to 0. Okay, for n greater than 0. Those are the initial conditions. Did you all understand that?
No, I don't see why.
You want me to say that again?
I don't see why.
Okay. You see, we have said that y of x has this form.
Oh, okay.
Okay? And we look at these initial conditions. These initial conditions don't depend on epsilon. Okay? So if I simply require that y0, or a0, the thing we're calling a0, it's the same as y0, is alpha plus beta x, then it already satisfies these two initial conditions. And that means that for all the other a's, a1, a2, a3, they must satisfy these initial conditions. So if we impose those initial conditions, how do we require that a prime vanish at x equals 0? We just integrate from 0. Okay? Perfectly straightforward. And now I've calculated a prime. Now I integrate one more time. And I get a n of x is equal to the integral up to x dt, okay, times the integral from 0 to t ds, q of s, a sub n minus 1 of s. So that's the general solution right there. Got it? Do you all see that? This is the solution. All you do is you do integral, integral, and you get the next a. That's it. It's really straightforward. Okay, so now that we've gotten this far, let's ask, does this perturbation series converge? Let's write down, what is the formula? I mean, if we iterate this now, what do we get? What's the formula for the nth coefficient, a sub n? What's the general formula? Let me stick it over here so you can see it. A sub n. What is a sub n of x? Well, if we do that n times, there's going to be some minus 1 to the n. And then we're going to have integral, integral, q. Integral, integral, q. Integral, integral, q. Integral, integral. N times. Okay? And then the last one is going to be integral, integral, q times alpha plus beta s. Okay? And that's it. That's the formula. So we solved an infinitely difficult problem by reducing it to an infinite sequence of easy problems. But here's the question. Does this perturbation series over here, does it converge? Now, I hate doing rigorous mathematics, but when it's easy, I'm willing to do it. Okay. So I'm going to show you that this perturbation series converges. So the question is, how big is a sub n of x? How big does that get? Okay. So if I take absolute values, okay, this is less than or equal to, if I have an integral and a function and an integral and a function, you know, you've learned bounds on integrals, right? If I have some integral of f of x And if f of x is bounded on some interval by m, then the integral, let's say from a to b, okay, you know this integral in absolute value is less than or equal to a minus b, okay, the length of the integration path, right, times m. Right? That's just a very coarse, rough bound. Does everybody agree? So how big can A be? Well, if the maximum value of Q, is m, that's how big the function Q can possibly get. And let's say the maximum value of alpha plus beta x, if the maximum value of that is, say, m, then how big can this integral possibly be? It can't be any bigger than m to the power n, because there are n different q's, right, times m, the maximum value of just the function alpha x plus, alpha plus beta x, right? That's how big that is. Times integral, pairs of integrals, blah, 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 blah. And there are altogether 2n of those integrals. Now, do you know what you get if you do that integral? If I integrate from 0 to x ds, and then from 0 to s dt, and from 0 to t du, and from 0 to u dv, and so on. What does that give me?
1 over 2n factorial?
1 over, exactly right. Say it again louder.
1 over 2n factorial.
1 over 2n factorial. Times, of course, the last evaluation, which is x to the 2n, right? Right. Very, very good. Very, very good. So this thing is just 1 over 2n factorial times x to the 2n. So what we have just shown is that the nth term in the perturbation series is smaller than some constant to the n times some other constant, which we don't care about, times x to the 2n times 1 over 2n factorial. So this perturbation series, this is fantastic. This perturbation series converges faster, no slower, than the series some constant to the n over 2n factorial. That's how that perturbation series times epsilon to the n. So what's the radius of convergence? Say it again.
Infinity.
Infinity. It converges for any epsilon. Boy, are we powerful. We can do anything. Right? Do you see that? So this is an incredibly hard problem. Right? I showed you that this is not a problem you can solve. But if we do perturbation theory, we can reduce the problem down to a trivial sequence of integrals, and the perturbation series converges for any epsilon. So we have completely killed this problem. Unless, what? Unless there's one possible way we might have a problem. You notice that in this constant to the n, there's an x to the 2n. Okay? So we can't let x be infinity. Okay? So it means we can't solve the Schrödinger equation on an infinite domain. We can only solve it on a finite domain for finite x. We can't use this solution all the way out to infinity, but unfortunately, when you solve the Schrödinger equation, That's exactly what you do, right? You require that the eigenfunctions are normalizable. So when you integrate them from minus infinity to infinity, they come out to be the integral of the square is finite, right? They're square integrable. And so on the finite domain, we've solved the Schrodinger equation, but not on the infinite domain. Okay, so we're not that strong. Okay, let me see. How does this work? Let's see. What happens? All right. Terrific. Okay, great. Yeah, this is good. Okay, so, but do you see how powerful we are? Okay, with one day's practice doing perturbation theory, we have now solved all possible second-order differential equations, at least on finite domain. That is fantastically powerful, right? Okay. So let's, now that we're feeling very strong, let's solve a really, really important problem. Okay? Let's solve an eigenvalue problem. Okay? So I want to now do quantum mechanics. And I want to show you quickly how you solve an eigenvalue problem. Okay? So the standard problem that you learn in quantum mechanics is this. You have a Schrodinger equation, d squared dx squared, plus some potential, v of x, okay, times an eigenfunction is an energy times that eigenfunction. This is the standard Schrodinger equation, okay? Now, there's one problem that you do know how to solve, okay? And that problem is where v of x is equal to x squared. Okay, and what problem is this? Say it real loud. Harmonic oscillator. You betcha. In fact, this is about the only problem we know how to solve. The only other one is the hydrogen atom. Okay, but this is the harmonic oscillator problem. Okay, and for example, if I put in a 4, I like to do just normalize it that way. Then the eigenvalues E sub n come out to be n plus 1/2. Okay, and you all have learned. Do you all know this? You all know that you can solve the harmonic oscillator. Does everybody know this? Are you comfortable with my saying that? Okay. Yes. That's not the right way to ask it. Would anybody like me to say a little bit more about that? Maybe I should put it in the positive. Because I don't want to put you in the position of admitting that you don't know something. All right. Okay, so imagine for a moment that you are walking down the street and some guy comes up to you and says, could you solve the following eigenvalue problem for me? Okay. And you look at it and you say, uh-oh, it's not a harmonic oscillator problem. It's some other problem, okay? In fact, this is a very famous problem. This is the anharmonic oscillator problem. Okay? It means that, this is Hooke's law. By the way, this is the potential. The force is the derivative. It's the negative derivative of the potential, right? So the force is minus v prime, right? So the derivative of this would be x over 2 with a minus sign, right? And that's Hooke's law, okay? If this term weren't here, you could solve it because that's the classical harmonic oscillator problem, minus x over 2. But there's this. So when you take the derivative of this, you get minus x cubed. And that is the next term in the Taylor expansion of Hooke's law for a spring, okay? So it's called the anharmonic oscillator. So it's the next correction to the harmonic oscillator. And this is very important in physics because not everything is a harmonic oscillator. but everything is approximately a harmonic oscillator. And what we are considering here is, you know, a deviation from the harmonic behavior. So if you have a pendulum is not a harmonic oscillator. It deviates, right? And there's an x cubed term. In fact, there's more. There's also an x to the 5 and an x to the 7. And when you add them all up, you get sine, right? That's the potential. Okay. So you think very hard and you say, wait a minute. This is a very hard problem. But maybe I can solve this using perturbation theory. Right? Where would you put an epsilon into this problem to be able to solve it? Yeah.
The x to the 4 term.
Absolutely. You're absolutely right. You would put an epsilon over here. So why would you insert an epsilon? Because you know that step 1 in perturbation theory, it must be that in the unperturbed problem, if you set epsilon equal to 0, you can solve it. And you can solve it. So that's the natural place for epsilon. So you have converted one problem into an infinite number of problems, each problem depending on epsilon. Okay? And of course, as soon as you put an epsilon over there, the energy is now a function of epsilon. Okay? Now this is a very interesting problem, and I'm going to show you the general procedure next time for solving this problem. But you know what you're going to have to do, right? What you're going to have to do is you're going to have to say E of epsilon is the sum from n equals 0 to infinity of, let's say, a sub n epsilon to the n. And psi of x, the eigenfunction, is also a series in powers of epsilon. So this is a sum from n equals 0 to infinity psi sub n times epsilon to the n. Now, if we were trying to find the ground state energy, ground state, we were trying to find the lowest eigenvalue, the ground state, can you tell me what is A0 and what is psi 0? Does anybody know? What is A0 to begin with? Say again, louder.
1/2.
1/2, that's right. 1/2. And do you happen to know what psi 0 is? In general, what are the eigenfunctions of the harmonic oscillator?
Gaussian.
Say it again. A Gaussian?
function.
Yes, times
Polynomial.
times Hermite polynomials. That's right. And if we're just looking at the ground state, the Hermite polynomial is just 1, right? So this is just e to the minus x squared over 4. And if you plug this into the differential equation, it's correct. Okay? So we know how to solve the unperturbed problem. So the question is, what happens? Okay? So I'm going to tell you the answer for this particular problem here. I'm going to tell you the answer. I'm going to tell you what happens if you do perturbation theory. I'm going to show you the technique for doing the perturbation theory next time. But I want to discuss, we're getting to the climax of this lecture, and I don't want to spoil the climax by rushing it. Okay? The climax is pretty cool. But let me tell you what happens if you just do the perturbation calculation. So you find that this perturbation series, remember we're calculating the ground state energy and also the ground state eigenfunction. Here are the first few terms in the perturbation series for the ground state. Okay? So the perturbation series begins 1/2. Okay? And then there's a number times epsilon. And that number happens to be 3/4 epsilon. Okay? And the next number happens to be minus 21/8 epsilon squared. And the next number happens to be plus 333 over 16 epsilon cubed. Okay? Do you notice something?
It probably doesn't converge.
It probably doesn't converge. It's certainly clear that these numbers are growing very rapidly, right? That's true. And in fact, if we get to epsilon to the 75, something like that, this number is something like 10 to the 144. Okay. In fact, if you want to know precisely, for n much greater than 1, for n large, a sub n is asymptotic to minus 1 to the n plus 1 times a constant, which is the square root of 6 over I to the 3 halves, which is some constant. Doesn't matter. Okay. Times 3 to the n times gamma of n plus 1 half. That's the asymptotic behavior. Okay? So as n goes to infinity, a sub n goes like this. So roughly speaking, how big is n, gamma of n plus a half? What is, do you know what the gamma function is? It's like an n factorial. So this is very roughly n factorial times 3 to the n. Okay? So it means that this perturbation series, E of epsilon, is a series that looks like epsilon to the n times n factorial times 3 to the n times minus 1 to the n. Roughly, a series roughly of that form. What is the radius of convergence of that series?
0.
Say it again?
0.
0. So it doesn't work for any epsilon except epsilon equals 0. In fact, since this is a divergent series, you can't put an equal sign there. It's completely invalid to use an equal sign. So in fact, you have been cheated because you've been told all along, if you have a hard problem, all you need to do is perturbation theory. In fact, the reason I'm mentioning this problem to you is because you've had field theory, you've had some field theory, and you've studied a Lagrangian of the form grad phi squared over 2 plus m squared phi squared over 2, which is free theory. And then you've been told, oh, let's consider g phi to the 4. And this is a typical quantum field theory that you study, and that's exactly like that. It's precisely the same, except the only change is that g is what we're calling epsilon. And you've been told, how do you solve this problem? Feynman diagrams, right? You write down the Feynman diagrams. You sum over g to the n times the sum of the nth Feynman diagram. Okay, so Feynman, you sum up the Feynman diagrams having n vertices. And you're told that's the solution to the quantum field theory. And there's only one trick. This thing is approximately n factorial times a constant to the n. Just like that n factorial. There's no difference. Okay, except this is a model coming from a differential equation, and this is what happens in a quantum field theory. You've been cheated! You can't write an equal sign. Okay, the Green's functions, when you're calculating Green's functions, you cannot write an equal sign, because that's a divergent series. Okay? So everything you've been taught is garbage unless we can make sense out of this. Okay. So I said we were coming to an interesting point in the lecture. So what I want to talk about, let's see. Hello? Great. Okay. So the first question, of course the important question is, what do we do? Help! And I'm going to teach you that, because what we do is really, really interesting. But the first question is, why did it diverge physically? Is there a reason why the perturbation theory diverged? And let me give you the answer in this case, but then I want to give you a simple problem where you will understand that answer. Okay? So the quick answer here is, if you have a Taylor series, what is it that causes the Taylor series to diverge? You know some complex variables, right? The function is not analytic, so it has a singularity, right? So for example, if you have the function 1 over 1 minus x, okay, and you expand it in a Taylor series, the radius of convergence is what? 1. Why is it 1? Because this function in the complex plane has a singularity at the point 1. That's the place where this function blows up. And therefore, the Taylor series has a radius of convergence of 1, and this is the region where the Taylor series converges. If we have a Taylor series that has a 0 radius of convergence, that means there's a singularity at epsilon equals 0. Okay? So if this is the complex epsilon plane, there is a singularity right there in the epsilon plane at 0. Why is there a singularity at 0? Because something abrupt happens at epsilon equals 0. What is it that happens very abruptly in this problem at epsilon equals 0? What happens at epsilon equals 0? Well, for positive epsilon, when epsilon is positive, the potential looks like this. But when epsilon is less than 0, no matter how small it is in absolute value, as soon as it's negative, the potential looks like this. Over here, we have bound states. But over here, we don't have any bound states. Because if you put a particle in this potential, what does it do? It tunnels out to infinity. Okay, we have Hawking radiation. Okay, so it tunnels through here and it goes out to infinity. Okay? So when epsilon is positive, we have bound states. When epsilon is negative, we don't have bound states. So something abrupt happens at epsilon equals 0. That's why we have a singularity at epsilon equals 0. We lose those bound states. And that's the reason why this perturbation series doesn't converge, because something abrupt is happening at epsilon equals 0. The potential is no longer a confining potential that has bound states. Okay, did you understand that? But what is that singularity? Does it have a physical meaning? And in the last 5 minutes, I'm going to show you what the physical meaning is. But I'm going to save the discussion of this more complicated problem, and I'm going to explain to you what is going on at a really, really trivial level. Because in fact, the problem here is completely generic. It's true of any potential, any Schrödinger equation. It's a completely general problem. And I want to explain to you what the nature of the singularity is. Okay? So to explain it to you, let's consider the following quantum system. I'm just going to consider a two-state quantum system. Do you have a question?
Yes, I wonder, couldn't we make a disk with a hole in it to the next?
And get a Laurent series. Yeah, and that's an interesting idea. But the problem is, you can only do that if you have an isolated singularity, and it's not an isolated singularity. Okay, the singularity, there is a singularity at the origin, but in fact, there are actually an infinite number of singularities with a limit point at the origin. So the origin is not an isolated singularity. If it were, like a pole, then indeed you're absolutely correct. And the perturbation series would then be, we looked for a perturbation series in the wrong form, and it would be, instead of a Taylor-like series, it would be a Laurent series. But unfortunately, the problem is more interesting than that, and we can't, there is no Laurent. Okay? But I'm going to claim that these singularities have a really interesting physical interpretation. And to give you a picture of what is going on, let's consider a Hamiltonian of a two-state system. And just two states. So it's a 2x2 matrix, okay? And let's say the energy of one state, let's, like an electron, spin up and spin down. Let's say the energy of the first state is A, and the energy of the second state is B. So here's a Hamiltonian. Okay? That's not a very complicated system. So there are two states in the system, spin up and spin down. And the energy of spin up is A, and the energy of the spin down state is B. And that's it. Okay? But now I'm going to turn on an interaction. I'm going to let these states interact with one another with a matrix of this form. Got it? Do you all see that? Okay. I look at this problem and I say, oh, God, that's a hard problem to solve. I think I'll use perturbation theory. Okay? This is a problem I know how to solve because I wrote down the solution here, and I'm going to multiply this by epsilon. Of course, we know, and I can develop a perturbation series if I want. Okay? But the Hamiltonian, of course, we can solve it quickly. The Hamiltonian is really A epsilon C B, right? And if we want to find the eigenvalues, we need to take the determinant of A minus E, B minus E, epsilon C, and set that equal to 0, right? That'll give me the energies of this system. Got it? All right? So if I calculate the determinant, I get E squared minus A plus B times E plus AB minus epsilon squared C squared is equal to 0. That's the equation for the energies. And I hate to do this, but I'm going to use the quadratic formula. E is equal to A plus B plus or minus the square root of A plus B squared minus 4AB plus 4 epsilon squared C squared over 2. Those are the energies. Okay? Okay, you all with me? So these are the energies. Now, let's see. This can be simplified a little bit because I can rewrite this as A plus B plus or minus the square root of A minus B squared plus 4 epsilon squared C squared over 2. Okay. Is this an analytic function? If I were to expand this in a Taylor series of the form, A sub n epsilon to the n, would this have an infinite radius of convergence? If I wrote E of epsilon in a Taylor series of this form, would it have an infinite radius of convergence or a finite? Finite. Why is that?
Because it's an essential singularity.
It has not an essential singularity, but it's not an essential, but it has a It has a cut. It has a branch cut. And there are two singular points, right? So in the complex epsilon plane, there are singularities here and here where the square root vanishes, right? So the square root vanishes when epsilon, at these 2 points, when epsilon is equal to plus or minus A minus B over 2C. Do you agree? That is when the square root vanishes. So these are the two singular points.
Times I.
Times I. Sorry, times I. Okay? Does everybody see that? These are the locations of the two singularities. And these are square root type branch points. So I could put a branch cut over here if I like. Now, the question is, what happens if I start with epsilon, say, at some reasonable value, 1, and as an experimentalist, I change the dials in my laboratory, and I gradually move epsilon around here, and I go through the branch cut, and I come back to here. What happens? What happens when you cross this branch cut? What happens to the square root? It changes sign. Therefore, the first energy level becomes the second energy level. That's really interesting. Nothing became infinite. It's just that the first energy level analytically continues smoothly to the second energy level. These are the square root branch points that cause this series to diverge. If this distance is r, then the radius of convergence is equal to r, the distance to the nearest singularity. Okay, do you all see that? And these things, these singularities that cause the perturbation series to diverge, these are very interesting points, because if you go around those points, one energy level continuously deforms into the other energy level. And if you start at the second energy level and you cross the branch cut and you come back again, you go back to the first energy level. So, remember this. Quantum mechanics is not quantized. Because if I'm allowed to vary epsilon into the complex plane, you smoothly go from one energy level to the other energy level. And in fact, these singularities that I drew here are all an infinite sequence of square root type branch points, which I'm going to tell you more about tomorrow. And you can go from any one energy level to any other energy level smoothly and continuously. Quantum mechanics doesn't have discrete, isolated, independent energy levels. There's only one energy function. Don't write E plus or minus. There's not two different energies. There's just one energy function. And on the first sheet of the Riemann surface, this energy function is equal to E1. And on the second sheet of the Riemann surface, it's equal to E2. So quantization comes from counting the sheets in a Riemann surface. Quantization is a purely geometrical phenomenon, and it has to do, why are there distinct energy levels? Because there are distinct sheets in a Riemann surface. Okay, we're going to talk about this in detail next time. Okay? This gives you, as soon as we start doing perturbation theory, a whole world opens up, and we realize that different energy levels are not, they are not independent numbers like, you know, when I wrote down here, the energy levels of the harmonic oscillator are 1/2, 3/2, 5/2, 7/2. That's not true. There's only one energy level, and they're all analytic continuations of one another. Smooth analytic continuations. The example that I can give you is, have you ever driven on these parking garages? Okay, there's you drive around and around, and you go from the first level to the second level smoothly. You can drive there without breaking your car. Okay? All you have to do is to go through a branch cut, and you are now on the second sheet of the Riemann surface. Okay? And then you smoothly go to the next sheet, and smoothly go to the next sheet. The energy levels in quantum mechanics are continuous. They are not discrete. Not if we enlarge our way of thinking about the problem by doing perturbation theory, and by introducing this magnificent parameter epsilon, because it gives you a whole new way of thinking about the world. Okay? If you ask, what's the difference between an electron and a muon, which is just like an electron but heavier, and a tau, which is just like an electron but even heavier, they're just analytic continuations of one another. In the perturbation parameter, what's the perturbation parameter? Electrodynamics, alpha. Okay, so if you analytically continue in alpha, you get the different states of the theory, all of them. Okay, so I think that's a good place to stop. Yeah,
So can we predict new particles or the new resonances of the on?
that's an interesting question. I don't know. We should be able to, in principle. In principle. Okay, so next time I'll tell you about this in much more detail, but at least you see where we're going. It is absolutely amazing, right? We understand at some very, very deep level what is actually happening in quantum theory, right? Quantum mechanics is not just a bunch of isolated eigenvalues. They're all just one eigenvalue, one energy function with different sheets in a Riemann surface. But I will explain to you next time what a Riemann surface is, and we'll talk about that in great detail. Are there any other questions? Yeah.
Is there any nice way to view degeneracies in this way?
In fact, when you have a degeneracy, that's what happens right at that branch point. Because you have a degeneracy there. This is precisely where the degeneracy is. At that point, this square root vanishes, and the two energy levels are equal. Okay? So there are two kinds of degeneracy, and I'm sure you've heard the word. One of them is called accidental degeneracies. It could be accidentally that two energy levels of some complicated system happen to be equal. But it might not be at a singularity, at a square root type singularity. It might not be. The other kind of degeneracy is the interesting kind, and that's called an exceptional point. And these 2 points are often called by a lot of people, not by everybody. People fight about this, but some people call these exceptional points. And these are the interesting points, and these are the points that determine the radius of convergence of the perturbation expansion. Okay, the radius of convergence of this perturbation series is precisely A minus B over 2C. Absolute A minus B over 2C. That's the radius of convergence, positive number. Okay? Yeah?
The divergence series in one of your theories appears after you perform renormalization?
Oh, that's a wonderful question. Okay, so I didn't say anything about renormalization. Okay, so you might say, does renormalization make the perturbation series converge? Okay, and for the most part, this is an open question. Okay, that is, for sophisticated theories like electrodynamics, the answer is not no. Okay, however, for super renormalizable theories, for simple quantum field theories like that one in less than 4 dimensions, phi to the 4 theory, and for this one, renormalization does not change anything. The perturbation series still diverges. Okay, so what is the purpose of renormalization? The purpose of renormalization is to make each term in the perturbation series finite. Okay, we do renormalization because some of the graphs that are contributing to the nth term happen to be divergent. So we renormalize, and now it becomes, this is now a finite number. Okay, but the perturbation series still has a 0 radius of convergence. And renormalization in general does not affect the fact that the series has a